Okay, everyone, any issues in lab? Any questions, any problems? Okay. So last week we had quiz 4. I'll go over that quickly and then we'll get into the next topic. So first question said, what's the next state function of state bit Q0 in the circuit below? So we've got 3 state bits, Q0, Q1, Q2, each are coming out of a flip-flop. So the Q0 state is coming out of the, this is the current state, it's coming out of the output of the flip-flop. And the input into the flip-flop would be the next state, right? So the input is A ANDed with Q1 or Q0, right? So Q1 or Q0, so that's the current Q1 or the current Q0 ANDed with A, which is the input, right? And that's the next state, that's for Q0, and then I've got the next state logic for the other 2 bits there as well. In the circuit below, suppose we set the A input to a constant 1 and then pulse the reset input. What is the state of Q2, Q1, Q0 in the third cycle? Recall that the S and R register inputs indicate set and reset respectively. So we've got, when we reset, we're going to initialize Q2 to be 1 because the reset's plugged into the set input, which will initialize that guy to 1, and Q0 will be reset to 0, and Q0 will be reset to 0. So our initial state will be 1, 0, 0. The next state will be determined by the next state logic that I had on the previous slide. So the next Q2 will be not A. A is a constant 1, so the next Q2 will be a 0. The next Q1 is going to be Q2 and A. So Q2 and A, that's 1 and 1 is 1. And the next Q0 will be Q1 or Q0. So basically 0 or 0, which is a 0. And then that's ANDed with A, which is a 0. So 0, 1, 0. And then in cycle 1, the next state, 0, 1, 0, will be transferred down into the current state. And then you just repeat this process to get the next state. And then finally, we get the third cycle, 0, 0, 1. Make sense? Okay, all right. Okay, for the finite state machine below, what is the output of the next state logic with inputs S0 equals 0, S1 equals 0, S0 equals 1, and A equals 1. So for this, we need to, the next state logic is the transitions, right? The edges, the arcs between states. And so S0 is 0, and S1 is 0, and S0 is 1. So we're looking for the state 0, 1. So that would be this guy here, 0, 1. This is the second state from the left. And then if we want to know what the next state is, when A is 1, so A is 1 would be this transition back to 0, 0. You see that? So basically we found the state that we're in. The current state is 0, 1. The next state would depend on what state we're in as well as what the value of A is, the input. So that would activate this left transition back to 0, 0. So the next state logic would be 0, 0. Okay? Yes?
So what is S0 and S1? So shouldn't the S0 be X1 to give the third state?
S0, oh, I'm sorry, 0, well no, S1 is the most significant bit of the state, and S0 is the least significant bit. I guess that wasn't really clear here. I should have subscripted those. I guess if it was S sub 1 or S bracket 1, it would have been more clear. But yeah, it's 0, 1. It's this guy here. Consider the system Verilog module below. What is the problem with this design? Okay, so we've got an FSM. We've got current state, next state, both 2 bits. We have our clock logic. that transfers next state into current state on the positive edge of the clock. And then we have our next state logic in this always COM. And then we have another always COM here that determines the output. Output logic? Right. So the output logic is foo, which is the output, equals next state. Okay. Now that's a little bizarre, but you can do that, except the problem is that next state is a 2-bit value and foo is a 4-bit value, right? So that's an issue, right? Is that right? Did I get that right? Yeah, next state, these are 2 bits, foo is 4 bits. So let's see, our options here are nothing, or not all always blocks are clocked. Well, that's okay. That's not a problem because the only clocked always block should be the clocked one, the one that sets the current state. The next state logic and the output logic are asynchronous, not clocked. So that's okay. There is a clocked always block. Well, that's fine. That's to be expected. Output logic has a latch. Does it? No? It just says foo equals next state. A latch would imply, yeah, the output logic is always COM foo equals next state, right? So that's not a latch. That's a latch would be if we had like if we didn't assign foo in every possible control path, right? Next state logic. Yes. The next state logic has a latch. Yes, there you go. That's true, right? We have an if statement and we don't have a default for the next state logic. So yeah, that's correct. The next state logic does have a latch because, yeah, there's no else. There's no default value for next state if none of the if conditions match. So that's correct. There are no inputs. Yeah, there's an input. Go is the input, and there's no output logic. There is. So yeah, the next state logic has a latch F. But I guess did I not catch the width difference there? I guess I didn't catch that, right? Because foo is 4 bits and next state is 2 bits. I guess I missed that myself. But yeah, so the answer there would be F, right? Of course, yeah, I think the Blackboard randomizes the order of the answers, so it may not be F in your case. You're designing an FSM to keep track of the mood of 5 students working in the digital design lab. This is from the textbook, by the way, this question. Kind of a silly question, but each student's mood is either happy, sad, busy, clueless. So the moods, there's 1, 2, 3, 4, or asleep. So there's 5 moods. What's the minimum number of bits necessary to represent these states? Okay, so the problem is that you could design this where you had a separate state machine for each student, right? Or you could design one monolithic state machine. In this case, we're creating one state machine that has to keep track of the moods of all 5 students. So you have to be able to keep track of every possible assignment of mood to all of the 5 students, right? So in this case, there's 5 moods and there's 5 students. So it would be like 5 to the 5th power, right? Possible enumerations, right? Which is whatever that is. What is that? 5 to the 5th power. And then you have to take the log base 2 of that to get the number of bits. Make sense? Right, I don't know what the answer is. I don't have it on there. And then consider the FSM circuit below. Which of the following describes the next state logic for S1? S1 is just, again, you're just looking at the input to the S1 register. It looks like it's there's an OR gate and it's ORing S0 or not S1, right? Yeah, so you just have to kind of trace backwards. Okay. All right, that's the quiz. Okay, so the next topic is circuit timing analysis. I think this is my favorite lecture. So I mentioned at the beginning of the semester that you have a logic circuit in like Verilog, for instance, and you've got inputs and outputs which are defined on the module line. Then there's some functional specification that's in the module definition. And I also mentioned that there was a timing specification, and we haven't talked about that yet. the timing specification is something that is related to the physical technology that you're deploying the design in, right? So for example, for combinational logic, the timing spec might be the propagation time, how long it takes to propagate changes in the inputs to affect the outputs, right? And for sequential logic, it could be the minimum clock period, how fast you can run the clock, right? So these are just differences between physical and behavioral aspects of a design. So the behavioral considerations are, does it work? And that's pretty much all we focus on in this class. So in this class, you design your CPU in Verilog and you simulate it in the simulator, but we don't really worry much about the physical aspects, like how much of the FPGA it uses or how fast it runs or how much energy it uses and that kind of stuff. Unfortunately, that would be something that ideally we would get into, but we don't really talk much about that or work with those things in the lab very much. We just assume that the design will work at 50 megahertz, and we just kind of and 50 megahertz is a slow enough clock that it's fairly safe assumption that your CPU will run at that speed. We're not really trying to push it beyond that. But as I mentioned, there are a lot of physical considerations like energy efficiency and speed and that kind of stuff. I also talked about how when you simulate, because we're just doing a purely functional simulation, that the simulator kind of lies to you in a way where it implies, if you look at the timing diagram, that there's no delay or there's an infinitely small delay between an input changing and the corresponding output changing if you have, like, say, in a combinational logic circuit, right? So I call this epsilon delay, which is essentially you have to run the simulator in order to see that output change as a result of the input changing. But you can run the simulation for as little time as you want, right? There's no lower limit on how long you have to advance the simulation in order to see an output change as a result of an input changing, right? So, and again, this is just because it's purely functional. We're checking the behavior of the circuit. We're not really concerned how fast the circuit is. But in reality, fundamentally, the way the digital logic works is by charging and discharging capacitors, essentially. And there's this, essentially the time it takes to charge a capacitor up is, it turns out, is the capacitance times the resistance. It's RC delay. It seems like, wait a minute, ohms, resistance is ohms,
Yes.
right? Capacitance is farads.
Yes.
And when you multiply those together, you get seconds? But yeah, that's just how it works out, believe it or not. There's this RC constant. Capacitance is higher when you have a longer wire, like when you're basically, like when you have fan out or a long trace, a long wire, that affects the capacitance and the resistance, right? And so what ends up happening is, and of course the logic gates themselves have internal capacitance on the inputs, and on the outputs they have capacitors in there. Those capacitances are much greater on an FPGA than they are in an ASIC, for instance. That's one of the reasons why people just don't use FPGAs for all digital logic, because FPGAs are about 10 times slower, right? You pay that, the reconfigurability comes at the cost of reduced density, logic density, which translates to longer wires and thus higher capacitance. And so FPGAs run generally at about 10 times slower clock rate than an ASIC, and you have about 10 times less gates on the FPGA than you would on an ASIC of equivalent size. So what ends up happening in general, whether you have an FPGA or an ASIC, if you have, say, for example, a buffer or any kind of logic gate, you'll change the input will change, and the output will correspondingly change. But there'll be a delay between when the input changes and when the output changes. And even changing the input and the output takes time. There's this rise-fall. So you see that the slope of this line is not exactly, it doesn't go straight up. It takes some time to change the input, it takes some time to change the output. But if you measure the time delay between the midpoint of the input transition to the midpoint of the corresponding output transition, that's often called the propagation delay, right? That's how long it takes for the input to trickle through the circuit and get to the output. So that's the propagation delay. More specifically, is the maximum amount of time it'll take. Because as it turns out, sometimes, depending on what input you change and how you change it, whether it's a rising edge or a falling edge, or which input you change if you have more than one input, the delay can be different. And so there's this notion of propagation delay is the maximum amount of time, the worst possible case, for how long it will take from the time you change an input to the corresponding output. And again, that may depend on what input you change or under what conditions you're running the circuit, right? But then there's this thing called contamination delay, which is the minimum amount of time. So the contamination delay is kind of the best case delay through the circuit, and the propagation delay is the worst case delay through the circuit. So you know when you change an input, the amount of time it'll take to propagate to the output will be between the contamination delay and the propagation delay, right? It's just basically a range of time. Make sense? Okay, so why are these different? Oh, by the way, the notation gets a little bit complex here. So I want to point out the propagation delay is T sub PD, and the contamination delay is T sub CD. Now, on Blackboard, on the quiz, and there's a quiz on this, by the way. We have a quiz due on Friday on this material. I'll use underscore. Like I'll have T underscore PD and T underscore CD. And on the slides, I show those as subscripts, right? So you've got PD and CD. And as I mentioned, sometimes if there's a difference between when you have when you change an input by bringing it up to 1 or bringing it down to 0. There's different paths through even a single gate. You'll have different paths, different lengths of wire, and different capacitances and different resistances through even a single logic gate, depending on what input, if you have multiple inputs, right? Now, again, this example had one input and one output because it was just simplified. But of course, gates usually have more than one input, right? So different inputs may have different delays to the output. And also, like even the operating conditions. If you run the circuit in a hotter environment, it'll be slower than in a colder environment, which is why, I don't know if you might have noticed this when you synthesize your designs on the FPGA, they actually have different timing models based on different temperatures. They have like a 0 degree and an 80 degree Celsius model. And then that's just for one gate. And then if you have multiple gates, if you have a circuit and you're calculating the delays through the circuit as opposed to the gate, like a circuit might have multiple gates connected in series and parallel, then there's different paths through the circuit. So generally, you're going to see a wider gap between contamination and propagation delay for a circuit as you would for a single gate, right? Because circuits are more complex. So here's an example of a circuit. So this guy has 3 gates in it, and you can see that if the D changes, if the D input changes, that D only has to go through one gate to make it to the Y, right? Whereas if A or B change, they have to go through 3 gates. So we have an imbalance in this circuit where we have a long path from A and B to Y, and there's a short path from D to Y. So the long path is usually called the critical path, and the short path is called the short path. Okay? So you can calculate the propagation delay of this whole circuit by adding up the propagation delay of the 3 gates along the critical path. So the overall propagation delay is the propagation delay of the AND gate times 2, because you have to pass through 2 AND gates, plus the propagation delay of the OR gate, right? And then the short path will determine your contamination delay of the circuit. So the contamination delay is going to be the contamination delay of the AND gate, right? So when you calculate the overall propagation delay, it's the sum of propagation delays on the long path versus the contamination delay of the whole circuit is the contamination delay, the sum of contamination delays of the short paths, right? And it's very common to have these imbalanced type of circuits when you synthesize your designs on the FPGA. So this was my attempt to try to characterize how complex this can get. So in this case, we've got, this is another circuit. There's only 3 gates in it. But I calculated 7 different paths through this for only 3 gates. And I color-coded each one of those paths to show there's 7 different ways that you can go through each of these gates. And then the number of paths is actually an exponential function of the fan-outs along each path. So every time you have a fan-out, meaning you can see this is a fan-out because this gate has its output going to 2 different places, right? That's a fan-out. Those fan-outs, every time you have a fan-out, it's going to create a branch, right? And then you can have another branch along that fan-out. And so in this case, I calculated the fan-out where fan-out of 0 means there's no fan-out, right? There's just only one. So for example, the fan-out of the fan-out of D is 0 because D to Y has no fan-outs, right? But the fan-out of A, B, and C is all 1 because basically A, B, and C all pass through this one fan-out, right? And so if you add up 2 to the power of the fan-out seen by each input, you can get the total number of paths through the circuit, right? So as you might imagine, the total number of paths, increases pretty quickly, right? As you increase the complexity. Now, one of the consequences of this are called glitches. So in this circuit, we have this unbalanced circuit where we have a critical path going through 3 gates and a short path going through 2 gates, right? Now, the problem here is that if you change, what happens is you've got B and not B connected to 2 AND gates, and the output of those AND gates go into an OR gate. So what ends up happening is that if you change B essentially makes the output of these 2 AND gates mutually exclusive, because if you set B to 1, assuming A is 0, right? If A is 0 and you set B to, and if C is 1, so if A is 0 and C is 1, let's assume that for the minute, then B, if B is 1, it'll set the output of this bottom AND gate to 1. And if you set B to 0, it'll set this top AND gate to 1 and the other one to 0. So what ends up happening is if A is 0 and C is 1, you set up this situation where if you change B from 1 to 0, you'll switch from this row of the truth table, right, 0, 1, 1, which gives an output of 1, to this row of the truth table, which is 0, 0, 1 with an output of 1. Now you would expect, well, it doesn't make a difference, right? Both truth table rows have an output of 1, so changing B should not actually affect the output at all, right? But the problem is because you're changing the inputs to this AND gate from 1, 0 and 0, 1. But when you change it from 1, 0 to 0, 1, there will be a period of time where the top input into the AND gate will lag because you're going through an additional gate delay. Okay, so essentially what's happening here is that if B starts out high and it drops, if the 2 outputs of these 2 gates, these 2 AND gates, is N1 and N2, right? Now we know, of course, that one of them is going from 0 to 1 and the other one's going from 1 to 0 because they're kind of, mutually exclusive, right? Because of the B being inverted going into one of them, right? What happens is that N1 will change actually later than N2 because N2 is a shorter path. So N2 will drop before N1 rises, right? So basically N2 and N1 are switching, right? They're both switching opposite one another. But because N2 is faster, it drops before N1 can rise, you end up with this output OR gate is going to see a 1, then it's going to temporarily see a 0 until N1 catches up and finally energizes, and then it'll go back to 1. So what you'll see in this case is that you'll have a glitch in Y, where even though I'm going from one row of the truth table to another, and both rows of the truth table have a 1 as the output of the circuit, you're going to see a weird little glitch here, right? Where the output will go down and come back up, right? Yes? Sorry?
If we have clock, won't Y will be updated after the clock?
Yes. Yeah, you will, but this is, we don't have the clock in here yet. We're just looking at this as a combinational circuit. And I don't know if any of you guys noticed this, but Model Sim, or QuestaSim, Model Sim, it actually simulates glitches. Sometimes you'll be simulating your circuit and you'll see these glitches. You'll see little weird glitches in the, I don't know how exactly it determines that, because the glitches are really a technology, in order to get a glitch, you have to map these to gates and find the paths through the gates, whereas Model Sim is just doing a functional simulation. But yet somehow it's still, sometimes you'll see glitches in there, right? So is there a way, first of all, is there any way to fix the glitch? Well, the book says that the reason the glitch happens is because if you remember from 211, and you have this Carnot map, this circuit is kind of the result of this Carnot map, where you basically have two terms. The terms are circled. These are the min terms that you've circled. And so you've got one term that is not A and B, B and C, right? So that's the bottom one, right? Yeah, B and C. So this circled term is the bottom AND gate, right? And then this circled term is not A, not B, right? So this circled term is the top AND gate. And so when you change B with A being 0 and C being 1, you're basically jumping from this entry in the Carnot map to this entry. So you're going from one grouping to another in the Carnot map, right? And so one way you can address this is you can insert a redundant term that covers that transition. So when you make that transition, in other words, by changing one input, it makes it impossible to entirely jump from one grouping to the next. So you can cover this term, which is where you have not A and C, right here, where you circle this. So basically you add a third term that doesn't change the behavior of the circuit, but it prevents the glitch from happening because it avoids you from having, it avoids the ability for one input to jump from one grouping to the other. Okay. Now, as you mentioned, glitches don't really cause a problem if you have the logic in the middle of two registers, two flip-flops that are clocked, right? The idea is that we don't really care if there's glitches, because generally the glitch is going to happen in between the contamination delay and the propagation delay, right? So by the time the propagation delay elapses from the time you change any input, the glitch will have worked itself out. In other words, the glitch will have corrected itself, right? So glitches will happen during that period between the contamination and the propagation delay, right? And so if we design the circuit to where we only sample the output of the combinational logic after the propagation delay, then we could ignore the glitch, right? We'll just assume it's not a big deal. hand wave it away. Okay. Okay, so, but we have to talk a little bit about guaranteeing that. So one of the other things you have to consider, there's two more terms here, two more parameters, two more technology parameters. The flip-flop itself has its own propagation delay and contamination delay. Why? Because the flip-flop is just gates, ultimately, right? The way you build a flip-flop is by taking logic gates and cross-coupling them, connecting them where an output of one gate feeds into the input of another and vice versa, right? You create a cross-coupled arrangement of logic gates to create a flip-flop. And the flip-flop is supposed to update its output after the clock edge, right? So you get a rising clock edge and it updates Q. But not right away because it has its internal delay, right? That's called PCQ, TPCQ. This is propagation, I don't know what the C stands for. PCQ. That's the propagation delay of the flip-flop, right? Likewise, the flip-flop also has its own contamination delay, which is TCCQ. Okay? So you just have to kind of recognize that PCQ and CCQ are the propagation and contamination of a flip-flop. Now, it's important to understand that you can't change these because the flip-flop is a building block. The flip-flop is given to you by the technology library of whatever platform technology you're using. So in the case of a FPGA, the flip-flops are literally baked into the FPGA, right? So the performance of the flip-flop is determined by whoever designed the flip-flops on the FPGA, right? There's nothing you can do about this. This is just fundamental to the FPGA. It's a constant. These are constants, right? Now, likewise, even on an ASIC design, generally when you design on an ASIC, you design with what's called a standard cell library. So you will synthesize your designs onto an ASIC. The flip-flop will be part of the standard cell library. So again, unless you want to create your own optimized flip-flops, which hardly anyone does, because you go to TSMC will give you the standard cell library that you will feed into your synthesizer. And so again, even on an ASIC, you have these are basically constants that you have to deal with. Okay. Now the problem is flip-flops have another property that you can't change, which is called the setup and hold time. The setup time is how long the input into the D input has to be stable prior to the clock edge. Now, when do you know the clock edge happens? Well, the clock edge happens when the clock passes the halfway point between power and ground, right? So whatever half the supply voltage is, whenever the clock passes half the supply voltage, that's considered to be the time of the clock edge. And so the input has to be held. You don't want to change the input to the flip-flop while you're clocking it on the edge of the clock, right? So the setup time is the amount of time that you have to stabilize the input into the flip-flop prior to the clock edge, and the hold time is how long it has to be stable after the clock edge. So the combination of the setup time, which is how long we have to keep the input stable before the clock edge, and the time you have to keep it stable after the clock edge, is called the aperture time. So, see, I would have called it, obviously this is an analogy to a camera. You snap a picture on a camera. Cameras have apertures. And so when the shutter is open is when you're recording, what the image is on the sensor, right?
if you have any kind of movement during that time, you get motion blur, right? And so if you want to freeze motion with a camera, you don't want any movement when the shutter is open, right? So what they should have called this was the shutter time, not the aperture. I don't understand, like, okay, cameras have apertures, but the analogy is shutter time, right? This is how long the shutter is open on your camera, during which you don't want any movement, if, assuming, of course, your goal is to freeze the action. You don't want blur, right? So, but anyway, the term is aperture. So the aperture time is the setup time plus the hold time. The setup time is T sub setup, and the hold time is T sub hold, okay? So basically, you don't want the input to the flip-flop changing during the aperture time. And the aperture time is around the edge of the clock, not necessarily centered on the edge, but it's around the edge. It may not be centered. These may not be, setup and hold time may not be equal, right? So it may not be centered, right? Okay, so there's this notion of dynamic discipline that says that when you generate a sequential circuit, now remember in the last lecture we talked about sequential logic design, what you can use sequential logic for, state machines and pipeline data paths and that kind of stuff. But the dynamic discipline determines how you generate the actual logic for a sequential circuit at the gate level. Now, luckily, you guys don't usually have to worry about this much because the CAD tools are doing this for you, right? The synthesizer is doing this. So Quartus is doing this for you. It's worrying about this so you don't have to. But you may have to worry about it if your system Verilog is trying to do too much inside of one clock cycle, right? In which case you may not be able to meet timing. The CAD tool may not be able to help you. In other words, the CAD tool may be, when I say the CAD tool, I'm talking about the compiler, the synthesizer, right? The synthesizer may not be able to synthesize the logic to obey the dynamic discipline depending on how much behavior you have inside of one clock cycle, right? Okay, so the dynamic discipline means basically that the logic should be synthesized such that you don't violate the setup and hold time for any flip-flops in your design. Okay? Okay, so basically when you synthesize the sequential logic, and again, this applies to like what I'm talking about here is if you design the stuff that we designed in the last lecture, and then you synthesize it, you end up with a design that looks like this, where you have flip-flop, output of the flip-flop goes through combinational logic. The output of that combinational logic then goes into another flip-flop, right? So this is your data path, and this is how your CPU works, right? For example, that first flip-flop is like, for example, your instruction underscore EX, right? And the instruction underscore EX has to go through sequential logic. It has to go through your control unit, right? Your control unit is combinational logic, and then your control unit generates basically a write enable signal, right? That gets clocked into a pipeline register for write enable, right? So that is one such path. Now, of course, there's a bunch of those paths in parallel. I think the critical path in your CPU, now I've gotten different answers on this. So this semester I asked Alex and one of my grad students to see if they could figure out, based on the output of Quartus, what the critical path is on the CPU that we design in this class. Where's the critical path? They gave me two different answers, unfortunately. So Soyasha's CPU, the critical path was in the branch resolution. So in your branch instruction, you start with instruction EX. That takes the register addresses through the register file, which is asynchronous, so it's combinational logic for all practical purposes. The registers come out of the register file, then they go into the ALU. Then you have to subtract them, right, to figure out if you want to take a branch, or if it's a branch if equal, a branch if not equal. You subtract, right, to figure out if the registers are equal. Then the value from the ALU goes back into the control unit and is compared to what branch instruction you're doing and it determines from the output of the LU what the program counter source, the PC source in the stall signal should be, right? According to Soyash, that's the critical path, right? That's what's going to limit your clock speed. So if you try to make the clock faster, if you say, well, I should be able to run this thing at 200 megahertz. Why am I running this at 50? Well, you're going to run into some trouble with that branch. So how do you resolve it? You have to go in and chop it up into multiple. You can't do all of that in one clock cycle. You can't decode the register values, ALU them, compare them, and determine if the branch is taken all in one cycle, right? Now the problem though is all of this dynamic discipline stuff happens at the gate level. But if you fail, if the compiler fails to enforce the dynamic discipline, then you have to go back and look at your Verilog, right? But the problem wasn't in the Verilog directly, it was in the gates. But you don't know how the Verilog was translated into gates, but yet the problem was in the gates. So you have to figure out how to change the Verilog in a way that when you resynthesize it, you have a shorter critical path, right? That's one of the big challenges of digital design, is there's that difference in abstraction between when the problem happens and the way that you have to fix it. You're fixing it at one abstraction level, but its problem is happening at another abstraction level, right? The problem is at the gate level, but you have to fix it at the HDL level. So it's tough. But anyway, okay, so so you have the clock period. The clock period is T sub C. That's another term, T sub C. That is the reciprocal of the clock rate. So at 50 megahertz, it's 20 nanoseconds. TC is 20 nanoseconds in your design. That's how long you have to get your propagation done, right, for your critical path. Now remember, the critical path is, sometimes hard to find, hard to identify. It depends on the gate level design. Okay, so we have this thing called the setup time constraint. The setup time constraint says that the clock period has to be greater than or equal to, in other words, the clock period has to be long enough to allow for the propagation delay of the flip-flops that are sourcing the input into the combinational logic. So remember, that's TPCQ. TPCQ is the internal propagation delay of this guy that's basically driving the input into the combinational. So pretty much everything starts with that, right? The timing path starts with how long it takes for the source register to get its stuff out onto Q, right? Then you have to add to that the propagation delay of the circuit, right? So again, this would be based on the critical path of the circuit, okay? Then you have to add a margin to this, which is the setup time. The setup time is how early you have to have the input into the destination flip-flop before the next clock edge. So this is a buffer, right? So you have to, these three terms, when added, have to be less than or equal to the clock period. Now, as I mentioned, you can't control this term. The propagation delay, this is not in your control. And you can't control this term, T setup, right? However, you can control this term, PTPD. This is the only thing you have control over. And as I mentioned, it's an indirect control, right? Because you're not doing gate level design, you're doing HDL level design. So you only have an indirect control over that because the synthesizer was what's actually generating the gates, right? But of course, there is a relationship between the HDL and the propagation delay, as I mentioned in your CPU. If you're trying to do ALU and branch resolution in the same cycle, then that's probably asking for trouble, right? Because that's a lot of stuff. Okay. So generally, they're going to rearrange this inequality. They're going to put the propagation delay, which is the term you can control, you want to isolate this on one side of the inequality, right? Because we can control this. And we'll take all the things that we can't control and move them to the other side of the inequality. So these inequalities are the same. The only difference is that Oh, and also the clock rate, we assume that that's a constant, right? Because this is assuming that we have a particular clock rate in mind, right? We have a certain goal. We have a clock rate we want to hit, right? So this is our timing constraint, like in our case, 50 megahertz or 20 nanoseconds. So this is considered a constant, and these are constants. So these are on the right-hand side, and this is on the left-hand side. So basically, this is what the bound of your propagation delay is as a function of these constants that you can't control, okay? Okay, so now that's the setup time, but there's also a hold time constraint. And this one's a little crazier. So the problem is that there's a hold time. If that combinational logic in between the two registers happens to be too fast, right? Like say you have a path that's just a direct connection. Let's say, hey, I want to create a shift register, so I'm just going to connect a bunch of flip-flops in series, right? Well, that's a problem too. Because once this guy changes, if the signal zips across really fast to the D input on the other one, then the hold time will be violated because this guy will see a change too quickly after the clock edge. It'll see a change of its inputs too fast after the clock goes up, right? So that would be a hold time constraint, right? Now the hold time constraint is based on the contamination delay. So the hold time has to be less than the TCCQ, which is the contamination delay of the source flip-flop, plus the contamination delay of the circuit. And again, you can rearrange this in a way that gives you some kind of control, right? You put the contamination delay as kind of the onus is on you. So you put that on the left-hand side, and T-hold and TCCQ are constants. They're on the right-hand side of the inequality, right? So that's the hold constraint. Okay, so here's an example circuit. In this case, we have 4 flip-flops A, B, C, D that are driving the inputs, and X and Y are the 2 output flip-flops. So here we're given some parameters. These would come from the technology library. By the way, if any of you guys have tried to download Quartus to your local computer, your laptop, you might have noticed that it's like a 70 gigabyte download, right? It's obnoxious. It's painful. That's why we provide it for you in the labs. You can install it on your laptop, but have fun. It's going to take a while to download, unless you have a really fast internet connection. And even then, that doesn't help you because their connection is slow. Like when you download it from Quartus, you don't even get to take advantage of your expensive internet. You don't get the full download speed, right? Why is it so big? The reason it's so big is because there's a gazillion different FPGA devices, and every single one of them has all of these technology parameters that have to be stored, technology libraries. These parameters are different for every FPGA, and there's a gazillion of them. And there's a lot more than this. They have timing, every single component in the FPGA, of which there are hundreds, if not thousands, because there's LUTs and DSPs and the routing fabric, the switch boxes on the routing fabric, and the I/O pads. All of those things have these timing characteristics. And what ends up happening is that when you download Quartus, what you're really downloading mostly are all these technology parameters, right? Anyway, so for this particular FPGA, we have TCCQ is 30 picoseconds. This is the contamination delay, propagation delay, TPCQ. Again, these are for the flip-flops. The propagation is 50. So again, the flip-flop is going to change its output between 30 and 50 picoseconds. The T setup is 60 picoseconds. The T hold is 70 picoseconds. Okay? And then each gate, now again, on FPGA, these wouldn't be gates, these would be LUTs because you implement logic gates on LUTs. But on an ASIC, these would be gates, right? On a standard cell library, every gate would have its own contamination and propagation delay. Each gate has a TCD and TPD of 25 picoseconds and 35 picoseconds. That's the range of delays for gates. Okay, so the first thing you have to do is figure out what the setup time constraint is. So in this case, our goal is to basically figure out what is the smallest clock period? In other words, what's the fastest clock rate this thing will run at without violating the constraint? And so we're going to calculate TC, and so TC has to be greater than or equal. So this will give us a lower bound for the clock period and thus an upper bound for the reciprocal of the clock period, which is the frequency, right? So first of all, we have to calculate the propagation and contamination delay of the circuit. So remember that the propagation delay is you have to find the critical path. Critical path here is 3 gates. So if you add up the 3 gates, you basically multiply the propagation delay of each gate by 3, right? So 35 times 3 is your propagation delay. And the contamination delay of the circuit is the contamination delay of the short path, which in this case is just 1 gate. So the contamination delay of the circuit is just going to be 25, whereas the propagation delay is 35 times 3, right? Okay. Okay, so 35 times 3 is 105 picoseconds. That's the slowest the circuit will be for the combinational logic. Contamination delay is 25. That's the fastest that you'll get an output out of that circuit. Okay, so to calculate the setup time, we have to add the propagation delay of the flip-flop, which is 50, right? That's T PCQ, right? So the flip-flop is going to take 50 picoseconds to even provide an input into the combinational logic, right? Then the combinational logic itself is 105 picoseconds. And then the setup time is 60 picoseconds. So we add all 3 of those up, and it means that the clock period has to be at least 215 picoseconds, which is 4.65 gigahertz. Okay? Contamination delay, the hold time constraint, we have to check if the contamination delay of the flip-flop plus the contamination of the delay of the circuit has to be longer than the hold time. Okay? Now that contamination delay of the flip-flop is 30, contamination delay of the circuit is 25, 30 plus 25 is 55, and the hold time is 70. Well, we got a problem. That violates the hold time. So now you might say, wait a second, but what about the clock? Can't we just adjust the clock to fix that? No, because the clock is not even part of the hold time. We don't care. The clock period is not a factor in the hold time. That's only the propagation time, or the setup time constraint. The hold time constraint, we don't care about the clock. So what do we do about that? Well, pretty easy. The CAD tool would have to insert redundant buffers. You can add extra gates to lengthen the contamination delay, the short path. So notice that these are dummy buffers it puts in, and that basically only changes the contamination delay of the circuit. So if we assume that these buffers have a contamination delay of 25, then that means the short path is now 25 plus 25 is 50, okay? 50 plus the contamination delay of the flip-flop is 30. That gives you 80. And 80 is greater than 70, so we now met the hold constraint, right? So you're hoping that the hold constraint can always be addressed by the CAD tool. You hope, right? Although sometimes I still get hold violations in the CAD tool. I don't know why. But the CAD tool, in this case, solved that. Okay, but there's another issue called clock skew. So this is another issue you have to worry about. The clock comes in the chip, and then it has to be distributed to every single flip-flop on the whole chip. Now, on an FPGA and on an ASIC, you have a specialized clock network on there. That's a high-speed clock. It creates a structure called an H tree. the clock comes in and it splits into H's and then it splits into more H's. The idea is that you want to try to get the clock across the whole chip as fast as possible, but it doesn't matter because any flip-flop that's closer to where the clock pin comes in on the chip is going to see the clock edge before flip-flops that are connected to the clock farther away from the pin. It's all about distance. The farther you are away. Now you might say, come on, man, electricity travels at the speed of light. No, actually it doesn't. Because electricity doesn't travel at the speed of light. Electricity travels at the speed of however fast the capacitor charges that you're conveying the electricity on, right? Remember, there's that RC constant. Resistance times capacitance is the time, right? So it's actually much slower than light, actually, right? And it depends on how much capacitance. The more capacitance, the slower it is. So you have this clock skew. So what ends up happening is if you have a register feeding a circuit, a data path, that's closer to the clock, so the source register is closer to the clock pin. The destination register is farther from the clock pin, right? What will end up happening is the destination register is going to see its edge, the same edge. It's going to look like it's a longer clock period. In other words, what's going to happen is the rising edge is going to be seen by the source register closer to the clock pin before it's seen on the far away register that's farther from the clock pin. So if you have input register closer to the clock pin than the output register, it extends the clock period, right? But if it's the opposite, if my source register is closer to the clock pin, if my destination register is so close to the clock pin and my source register is far from the clock pin, it has the opposite effects. It shortens the clock period, right? Because what will happen there is that the source register will get a late start relative to its destination. It's like a race where you hold you start the race and you hold someone back for a little while before you let them go, right? That's what will happen. Yes?
Doesn't the setup time take too long?
No, you have to account for the setup time. The setup time, what the setup time is doing is if you have the situation I just described where the rising edge of the clock is coming later in the source register as it is in the destination register, right? Then that's going to act to compress the clock period, and it's actually going to make the setup time harder to meet, right? Because you have less time. In other words, the clock skew is going to make it look like there's extra delay coming into the combinational logic circuit. And it's not really extra delay, it's just extra delay as compared relative to when it has to be ready for the propagation delay, right? And then, of course, the opposite is true for hold time. If the source register gets a head start because he's closer to the clock source, then he is more likely then to violate the hold, right? Because it's going to speed up, it's going to give him a head start. He's going to get his signal out even faster as compared to its destination because he got a head start because he saw the clock edge first before the destination register saw its clock edge. So this is called clock skew. Okay, so basically the way that you take care of this is the clock skew is another technology parameter. So this is yet another part of that 70 gigabyte download that you get from Quartus. It's defined for every FPGA technology. It basically depends on the size of the FPGA and the technology of the clock buffers and how big the clock tree is. So basically that clock skew is a kind of a worst case skew. It's basically the worst case. It's kind of the amount of time difference between the clock rising edge nearest the clock pin and the clock rising edge farthest away from the clock pin as compared to the clock, as compared to the, or the amount of, as compared to like whatever the clock period is, right? So for the setup time, you basically have to add the skew as another parameter to consider that as a possible delay, right? So you've got the propagation of the flip-flop, the propagation of the logic, the setup time, and the skew. right? And again, this is assuming that the source register is lagging the destination register because the destination register is getting it's getting its clock edge first. I mean, just to clarify, ideally, every register on the FPGA sees the same clock, and they're all synchronized. When the clock goes up on one register, it's going up on all the registers at the same time. But the clock skew is saying that's not true. It's that when the rising edge of the clock comes, it's like a wave front. That rising clock kind of propagates through the whole FPGA, right? So when you do your setup time analysis, you basically have to account for that, right? So again, so you just account for that. And then for hold time, it's the same thing. For the hold time analysis, you have to build the hold time. You have to put the skew on the same side of the equation as hold time. Now this one's a little bit more confusing, right? So basically, the contamination delays are on one side of the inequality, right? So this is delay, right, on the left side. The right side is the earliest you can get the data through the circuit, right? So the skew gets added to the right-hand side along with the t-hold, right? Because this is defining essentially the shortest amount of time that you can contaminate. And then the two contamination delays are on the left side. But then, of course, in the end, you want to isolate the contamination delay because as a CAD tool or as a designer, this is what you have control over. And presumably, these are just constants that are baked into the technology of the FPGA or the ASIC. OK, so now let me talk about what happens if you change the input to a flip-flop during the aperture time. Does the chip explode or what happens? Turns out it's kind of subtle. If you change the input to a flip-flop during the aperture time, the flip-flop will go into a state called metastability. What it'll do is the voltage coming out of the Q output will go into the forbidden zone. The forbidden zone is between ground and VDD. So, it's supposed to be 0 or 1. It'll be between 0 and 1, right? But it's not going to stay there forever. It never stays there forever, ever. Eventually, it'll go out of metastability and it'll settle at 0 or 1, right? So you can think of it like a ball balanced on a hill. The ball will balance on the hill, but eventually will kind of roll down one side or the other, right? The question is, how long does it take for that to happen, right? Well, you might say, why do we care? The CAD tools are going to tell us if we violated the dynamic discipline, so we should never go into metastability. Well, yes. However, the CAD tools don't have control over inputs to your circuit. So if you design a digital circuit that has a push button, which actually you guys have, right? Your circuits have switches and buttons on the FPGA board that are fed directly into the FPGA, right? In fact, they're fed directly into flip-flops, right? They get latched, right? That's what happens when you do the CSRW instruction. It latches the switches, right? So you can't control that, which means that if you happen to flip the switch on the FPGA board during the aperture time, which of course as a user you have no idea, right? You have no idea if you're doing that or not. How would you know? You don't know what the clock is doing, right? Then the input will go into metastability. And your CSRW instruction will give you wacky results, right? Now this doesn't just apply to buttons. This applies to network packets coming in from your network, right? Your Ethernet card has data coming from external source that's not synchronized to the clock of the computer. So if a network packet comes in, there's no telling whether it'll violate the dynamic discipline. Ultimately, you just have latches that latch. Also, if you guys know about SPI and UART and I2C, and all the communication protocols that are used for chips to talk to one another on a circuit board, all of which could violate that dynamic discipline, and there's nothing you can do about it. And there's no technological way to design this flip-flop that makes it immune to metastability. Okay? So what do we do? That's just a depiction of metastability. Okay, so now I mentioned that the one thing we can leverage here is the fact that if you go into metastability, you will not stay there forever. Eventually, the flip-flop will come out of metastability. It turns out that the time it takes to come out of metastability is based on an exponential curve, right? So the probability that the resolution time is greater than t, which is the amount of time, my input, how long I'm considering, is e to the negative t divided by tau. Tau is, again, another technology parameter. So tau just defines essentially the slope of the exponential curve, right? It's the mean of the exponential, right? And this is, again, something that's baked into the circuit that makes the flip-flop, right? Okay, so what you do is you say, well, so I know that the amount of time it takes is based on this distribution. So what I can do is I could say, first of all, what is the probability that I'll go into metastability? So t sub 0, again, is another parameter. T sub 0 is the aperture time. That's simply the t hold plus t setup, right? T setup plus t hold is t sub 0. It's just the total aperture time. And t sub c is the clock period. So if you take the ratio of t sub 0, if you look at the ratio between the aperture time versus the clock period, right, then that gives you the probability that if you randomly switch the input sometime during the clock period, that it will happen to fall inside of the aperture time, right? So that's t0 divided by tc, okay? So if you then take that probability and you multiply it by this exponential, what that's saying is, what is the probability that I'll go into metastability, which is this, and I will still be in metastability after t seconds. When I say and, the and is multiplying probabilities. So again, probability I'll go there, probability I'll still be in metastability after t. That's why I'm multiplying, right? So you're multiplying these two things because you have to, first you have to get there and still be there at the end of t. Okay, so then what you can do is you could create a synchronizer. A synchronizer is where if you have an input, you add an additional flip-flop. So you take the input, like say from your buttons or your network cable or whatever, you plug those into a flip-flop, and then the output of that flip-flop gets fed into your real flip-flop. So basically what you're doing is you're protecting this flip-flop with an additional redundant flip-flop connected as a shift register, sort of, right? Two flip-flops connected in series. And what that's doing is it's saying that if the first flip-flop goes into metastability, then we're going to give it a whole clock cycle to get out of metastability by the time you get to the next cycle, which is when you clock it into the second flip-flop. Make sense? So this is just a protection, right? However, there's still a chance, even if you do this, that at the end of the second clock cycle, this first flip-flop may still be metastable, in which case now you're feeding a metastable signal into the second flip-flop, which, of course, will put it into metastability as well, right? However, this is the best approach. This is really the only thing we can do, right? And so, so we can calculate, this allows us to calculate basically how long it'll take before we can expect to have a metastability. Okay, so what that is, well, this is basically the probability of a failure on an input changing, on an individual input changing, on one. So if you put one input into that first flip-flop, the probability of the failure is going to be, of course, the probability of going into metastability, which is the aperture divided by the clock period, right? Multiplied by the time in which we want to be out of metastability, which is going to be the clock period minus t setup, and then divided by tau. Tau is just that technology parameter. That's the mean of the exponential, okay? So basically this is how long we have. If we have a synchronizer, right? If we have a synchronizer, then the amount of time this guy has, the first flip-flop, to get out of metastability is basically the clock period for the next cycle minus the setup time. Because of course, if it gets out of metastability within the clock cycle, but too late, and it violates the setup time, then of course, we consider that a failure too, right? So as long as this guy gets out of metastability by clock cycle minus setup time, we're good, because then he'll be out of metastability and we'll finally get the correct value in the second flip-flop, okay? Now, the question is, we have to consider how often we're going to change that input, right? So obviously, a network interface card is going to have bits toggling very, very fast, like at a gigahertz, right? Whereas if you have the FPGA in class and you're just flipping switches to do your lab 4, not very fast. You're not flipping the switches very fast. So depending on how fast you toggle the input, that will determine what the mean time between these failures are, right? So the mean time, or actually one way to do it is failures per second. So if you take that probability of failure and you simply multiply it by n, which is the number of toggles per second, that will give you how many failures per second you can expect to get, right? So basically you're just taking the rate at which you're changing the input and multiplying it by the probability of a failure. However, if you take the reciprocal of that, you can get the mean time between failures, right? As opposed to the number of failures per second, right? So basically take the reciprocal of this equation and you get how long you can expect on average between failures, right? What's a failure? A failure is just a corrupted data, right? So if you're designing an interconnect, like, excuse me, if you're designing an interconnect like UART, you might want to put a parity bit in there, right? That's what the parity does on a UART channel, is accounting for this metastability, right? Or you may need some other kind of error detection mechanism in an I/O, any kind of I/O. You know, chips talking to one another, they don't share the same clock, and thus they can't guarantee the dynamic discipline. Okay, so here's an example question for that. I only have a minute, so I'll rush through this really fast. So this gives you clock period 500 megahertz, clock speed 500 megahertz, 2 nanoseconds. Aperture time 150 picoseconds. Again, that's just setup plus hold. T setup is 100 picoseconds. Tau is 200 picoseconds. Now again, tau is just how long it takes the thing to get out of metastability on average. That's the mean of the exponential. That's just a technology parameter, but it is in terms of seconds. The units are seconds. And n is 10 events per second, 10 button presses per second. What is the probability of failure? What's the mean time between failure? Basically, you just plug those numbers in, and in this case, it's 5 hours. You can expect a failure every 5 hours in this scenario. Okay? Okay. Yeah, and then I just had another example here. Okay, so that's it for this lecture.